Good morning, my dear students. Coming to the another method problem, that is the second problems on penalty method problem. Okay, so in module 2 already we studied about what you mean by stiffness matrix and what is the importance of stiffness matrix and problems of handling the two boundary condition, that is elimination method and penalty method. Okay, so this is the second problems belongs to the penalty method problem. Okay, so here I am using all the images I copied from this textbook, that is SB Hall's textbook. Okay, so module 2 syllabus same. Okay, what I told. So here in the question they given like this. Okay, so this problems is very important for the point of examination. Okay, problem is given like this. Problem number 2, consider the bar shown in the below figure. An axial load P is equal to 60 into 10 to the power of Newton is applied at its midpoint using penalty and elimination method. Okay, so this problem can be solved by any one method using penalty or elimination method. Okay, so I am going to solve this problem by penalty method. So elimination method already we solved. Okay, of handling boundary condition, determine the nodal displacement and support reaction. Okay, so the main difference between I am telling again. So the main difference between penalty method and elimination method means, in elimination method the known values we are going to delete the respective row and column. Okay, in penalty method the known values we are going to add some value, that is maximum C values to the known values, then we are going to solve the displacement strain that reaction at each support. Okay, so here the question given. Okay, so diagram is given this. Okay, so here this is a 2D bar element. So here load is acting. So this first element, second element. So this is fixed at the distance gap of 0.12. So okay, the area for this element is given 250 and Young modulus is 200 gigapascal. Okay, so the length is given 150. Okay, so note down all the given data here. Okay, so that is what Young modulus for E is equal to, or so suppose they given common E, so no need to find the A1 A2, that is E1 E2, so common, that which is equal to both the element. Okay, that is Young modulus E is equal to E1 E2 is equal to 200 gigapascal, that is 2 into 10 to the power of 5 megapascal, and area of an element which is equal to same area 1 which is same as area 1 and A2, and length of each element they given 150, and the force acting at middle is this is not a 60, this is a 60 kilonewton. So I have to change here 60 kilonewton. This by mistake I wrote here. This is 60 into 10 to the power of 3 Newton. Okay, so now so have to resolve this force into what, have to compare the given problem, have to modify, that is step number 1. FEI model have to convert. Okay, FEI model for first element is discretization process. Okay, so here since it is considered 2D element because force is acting here, so this is first element, this is second element, so have to consider this first element and second element, and some distance they are fixed, this at a distance of 0.12, that is A3. Okay, so the 1 to 2 that is called as element number 1, and 2 to 3 we are going to call as element number 2. Okay, so Q1 is equal to displacement at node number 1 and displacement at node number 2 is equal to Q2. So here force is acting, that is F1 is equal to, and here force is acting F2, and here force is acting F3. Okay, so L1 L2, the distance gap is 0.12. so this is a finite element model for the given problem. Okay, so next second step is same procedure again. Since in the given problem there will be two elements will be there, have to calculate the element stiffness matrix for each element. So this is the standard formula. Substituting for first element, substitute all the values, area, E and length, that is 250 into 2 into 10 to the power of 5 150. So you simplify this, you are going to get 10 to the power of 5 into 3.33. so that 3.33 have to multiply inside, so you are going to get 10 to the power of 5 is equal to 3.33 minus 3.33 minus 3.33 3.33. Okay, so matrix close. So since it is belongs to first element, the nodes are present in the first element is 192, so write the global degree of freedom is 192. So I hope you understand this. Okay, similarly you have to calculate the second element. So replace here A2, changes the formula A1 to A2, that is A2 E2 by L2. So substitute A2 E2 value. Okay, so again you simplify this, 10 to the power of 5, same value you are going to get, that is 3.3 into 10 to the power of 5. Again you multiply that into in the matrix, you are going to get, so 10 to the power of 5 matrix of 3.33 minus 3.33 and minus 3.33 3.33 positive. So okay, here the global node vectors are what, 2 into 3. So because since it is belongs to the second element and it is connected 2 and 3, so right here 2 and 3 2 and 3. Okay, so once if you know the element stiffness matrix for each element, then go for calculating the global stiffness matrix. Okay, what is the global stiffness matrix? K is equal to K1 plus K2. Okay, so how to add, since it in this given problem 3 nodes are there, 1 2 3 are there, so first you have to write the 3 into 3 matrix. Okay, so addition means K1 K2 have to add it. So in the both the side the common is what, 10 to the power of 5, 10 to the power of 5 is there, right here 10 to the power of 5. Okay, so here how we got this 1 into 1, that is 3.3 means, so this first element is belongs to the node number is 191. Okay, so 191 you have to check again, so 1 and 1, So 3.33 here not there, so right here 1.1, that is 3.3. Okay, again 2 is minus 3.33, one thing what 2 and 1, so 2 and 1 minus 3.3 here not there, minus 3.33 plus 0 right here minus 3.33. So I wrote here 0, see 0 is 3 and 1. Okay, 3 and 1, so 3 and 1 here also not there, here also not there, so 0 plus 0 is equal to 0. Okay, like that you have to, I wrote here 6.66. okay, this is, it is belongs to 3, 2 into 2. So look at here, 2 into 2, 2 into 2, this is 3.33 plus here also there 2.2 and 2, so 3.33 plus 3.33, which is equal to 6.66. like that you have to calculate the global stiffness matrix. Okay, so nodal displacement vector is equal to what? Here 3 nodes are there, so U1, that is Q1, Q2, Q3. So after calculating the equilibrium conditions, check whether which method they are asking, whether elimination method or penalty method. Elimination method means same procedure, we have to delete the respective row and column, that is a fixed node, but here they are asking penalty method. Okay, so the step number 1 is equilibrium equation for the entire body is given by Q which is equal to F. So substitute all the values here, K values and Q values, F value. Okay, so it's from the figure Q1 which is equal to 0 and Q3 is equal to 0.12. okay, so from the figure Q1 is, that is a fixed, from the figure Q1 is fixed here. Okay, so Q1 equal to become 0, and here the Q3 value is 0.12 is there. Okay, that is 0.12, so they given in the problem. So right here Q 0.12 using penalty method of handling quantization. This is the formula, is their standard formula. C is equal to maximum of Kij into 10 to the power of 4. So in the maximum value from the global stiffness matrix is equal to 6.66 into 10 to the power of 5. Okay, so this is the maximum value. So substitute here, maximum value is 6.66 into Kij is equal to 10 to the power of 4 into 10 to the power of 4. So after simplification you are going to get C is equal to 6.66 into 10 to the power of 9. Okay, so this value you are going to add at the value third row, that is K11 and K33. Okay, so K11 K33 is nothing but what? So since it is belongs to the third element, that is, suppose if you consider this K11, K12, K13 and K21, K22, K23 and 31, 32, 33, the nodes are fixed at the third element. That displacement is given this element. This value is nothing but what? K13, K23, 33. Okay, so that we have to take here. Okay, so that those K11 and K3 they have to add, so the modified global stiffness matrix become like this. Okay, so this value 6.66 in 10 to the power of 9 you have to add here this node number, this and this. Okay, after adding, so the global stiffness matrix standardized is given by like this, and also the force vector changes to, this force vector is going to changes what? This vector is changes to F1, this F1, F2, F3 changes to this equation. Okay, so F1 plus C A1, F2 and F3 C A3. Okay, so since it is not added here, so only this one is fixed is there, this one is fixed there, so C and A1 have to add it. So A1 is equal to which is equal to displacement, that is Q1. Okay, so here A1 is equal to 0 but A3 is equal to 0.12 is there. Okay, so after substitute the formula, that is F1 C A1 is equal to 0, we will become 0, F2 they given 60 and A3 is equal to 0.12, C value is there. So after simplification, force value is become what? Force is equal to this equation, C 0, 60 into 10 to the power of 3, 799.96 into 10 to the power of 6. Okay, so now the modified global stiffness matrix changes to from beginning to like this. Okay, so now you can solve by solve this equation, that is a first row, first column, second row, second column, third row, third column. You are going to get the displacement on solving or simplification. We are going to get Q1 is equal to 7.50 into 10 to the power of minus 6 mm, Q2 is equal to 0.1500 mm and Q3 is equal to 0.1200 mm. Okay, so these are the nodal displacement for the given bar, that is we have to write in this fashion. Q is equal to, this is Q1, Q2, Q3 or U1, U2, U3. So this is your answer, displacement. Okay, support reaction, already we know that reaction in the penalty method formula we are going to use this R is equal to minus C, that is Qi minus Ai nothing but the number, that is a node number, that where I is the fixed node number. So here we have first node and second nodes are fixed, you have to calculate the first node and second node. Okay, so support reaction R1 is equal to minus C Q1 A1, so A1 is 0, so Q1 already we calculated, substitute C already we calculated, substitute his values in this equation, you are going to get R1 is equal to minus 499.79 Newton. Okay, that is 49,979 Newton, so which is acting opposite. Similarly at R3 is equal to same, you just replace R1 to R3, so substitute values, A3 is equal to minus 0.12, that is what? 0.12. so substitute here, you are going to get the R3 is equal to minus this, that is what? 10016.64 Newton. Okay, so support reaction at R1 and R3, these two are acting opposite to the support. Okay, so this is like using penalty method. Only penalty method is, this is the only difference. Okay, C maximum how to calculate, add there, and force value changes to this equation, the remaining procedure is same. Okay, so this is what the problems on penalty method by using what? The distance gap problem. Okay, so like this you have to solve the numerical problems on penalty method. So in this you have to concentrate, main thing is how you are going to add the values. Okay, first you observe the diagram, wherever fix is there you have to calculate the maximum C value, and you are going to add there. Okay, that is the own difference. Okay, you have to write, you have to note down, you have to calculate here in the modified global stiffness, that is global stiffness matrix. Okay, and also force value changes, whereas in elimination it is not like that. Okay, so just to directly wherever fix is there you are going to delete. Okay, so this is the only difference between penalty and elimination method. So read the question carefully, which method they are asking, according to that you have to solve. Okay, in the both the method, the up to 4 steps are that is step 1 2 3 4 are same. From 4th onwards only it is going to changes. Okay, so like this you have to solve the problems on penalty method. I hope this problem you understand. Okay, thank you.